minus 1 because the bottom is just a linear function. So this is just the natural log situation, and we have 2x minus 1. But because we have the 2 right here, so go ahead and divide it by 2, right? Because the derivative of 2x minus 1 is 2, so divide it by 2. And we are going from 1 to infinity. And technically, we don't need the absolute value because when x is going from 1 to infinity, the inside is always positive. But we can leave the absolute value there. All right, now let's just plug in. So we have 1/2 ln absolute value 2 times infinity. And remember, when you put in infinity right here, we are taking the limit, right? And then minus 1, so that's the first part. And then we're going to subtract, plug in 1, so we have 1/2 ln absolute value 2 times 1, and then minus 1, like so. Right? So right here, let's see. 2 times infinity is infinity, minus 1 is still infinity, absolute value of infinity is still infinity, ln of infinity is still infinity. Multiplied by 1/2 is still infinity. Yes, just infinity right here. This 2 times 1 minus 1 is 1, but instead of the ln, we get 0 times 1/2 is still 0. So this is just infinity minus 0, so we get the whole thing to be infinity. Therefore, that integral diverges. So as you can see, that infinite interval, when we go from 1 to infinity of this, we turn out to get an infinite area, right? Now, let's see the type 2 situation of the same function right here. We go from 1/2 to 1. Well, when x is 1/2, when we put it here, we get 1 over 0. We actually have a vertical asymptote. That's why, let me just emphasize this. We have a vertical asymptote at x equal to 1/2. That's why this is a type 2 improper integral, okay? So, same integrals, just go ahead and put that down, right? 1/2 ln absolute value 2x minus 1. And then we are going from 1/2 to 1 and plug in. And before we do so, let me just emphasize that because we do have a vertical asymptote when x is equal to 1/2. This right here is technically 1/2 plus because we have to take the limit. We have to think in terms of limit. All right. Plugging 1, we first get 1/2 ln absolute value 2 times 1, and then minus 1 in the absolute value, first part right here, and then minus, plugging 1/2 plus. So we have this times 1/2 plus, and then minus 1. Pretty good. All right, for this part, we get 0. For this part, 2 times 1/2 plus is 1 plus. So let me just write that down for you guys, and then minus 1. That will be 0 plus. And ln, absolute value of 0 plus. This right here is negative infinity. Now, remember, when you look at the graph of natural log, if x is approaching 0 from the right-hand side, the graph goes straight down. That's why we get negative infinity. And then, right here, we just continue. We have the 1/2 in front. So, of course, that's still negative infinity. But we have this negative in front. So all in all, we get a positive infinity. So 0 plus infinity, we also have infinity right here. Well, kind of weird. Both of them diverge, right? But that might not be the situation. Check out the other questions. This bottom can actually be factored in, so to go ahead and do that, we get x minus 1 times x plus 2. And notice when x is equal to 1, we will actually get the vertical asymptote. So that's why this right here is the type 2 situation, while this right here is the type 1 situation because we have infinite interval going from 2 to infinity. But when x is equal to 2, it's not vertical asymptote, right? All right, so to integrate this, we'll use partial fractions. Well, let's look at the integral going from 2 to infinity. The first fraction will have x minus 1 on the bottom, and the second fraction will have x plus 2 on the bottom. And to figure out this number here, we'll go back to the original, cover this up, and x has to be 1, and we put it there. 1 plus 2 is 3 on the bottom, so we have 1/3 right here. And then to figure out this, we'll go back to the original, cover this up, x has to be negative 2. Put it there, so we have 1 over negative 2 minus 1. So we have negative 1/3. So both of them have a third, right? And this is negative, and we can go ahead and integrate this. First, this right here is 1/3, and then natural log absolute value of x minus 1, and because this is just a 1, dividing by 1 doesn't change anything. And then next we have minus 1/3 ln absolute value of x plus 2, and that's pretty much all we have. And I'm actually going to put them together as one single logarithm, and then I will do the 2 to infinity, right? So right here, we can factor out the 1/3, and because we have this natural log minus this natural log, when you put them together, it becomes natural log of the first divided by the second, so x minus 1 over x plus 2, like so. So that's what we have. And then here, let's go ahead and plug in, right, 2 to infinity. So technically, I should also do that right here. And the reason that you want to do this first before you put in the limit, it's because if you put a limit in here and here, you actually get infinity minus infinity in the same parentheses. Well, in that case, go ahead and combine them and use the natural log property and do L'Hopital's rule if necessary. All right, the first trouble is when we put infinity into here, we actually get what though? Well, I will actually have to show you guys the work on the side just to be legitimate. We will actually have to take the limit, so I'll just put this down right here. So this is just a blue star. We have to take the limit as x approaching infinity. And let's just look at the first part, 1/3 ln x minus 1 over x plus 2. If you put infinity, you get infinity over infinity inside. That's why you have to put it on the side and do more work on that. Well, the truth is, when we have infinity over infinity, in this case, even though it's inside of the natural log, but you can still bring the limit inside and then do the L'Hopital's rule. Why? Because natural log is a continuous function, so you can just evaluate the limit inside. And when you do that, let's see if I put it here, that this is going to be, we have the 1/3 on the outside, and then ln absolute value. And again, I'm looking at the limit, but I'm putting the limit inside. And then x goes to infinity, and then we have the x minus 1 over x plus 2, like so. So that's pretty much what is happening. You do things inside out. And right here, if you put infinity here and here, well, you have two ways to do it. The first way is you can just do L'Hopital's rule. The second one is, because we have a power function over a power function, or polynomial technically, you can just pay attention to the dominating part of the top and also on the bottom. Well, technically right here is just going to be the highest power of x. And because they are both x to the first power, so you see this is just going to reduce to be 1. So all in all, this gets to be 1/3 ln. The limit of this is just going to be 1. So we have ln of 1, and then this is going to be 0, right? Therefore, when we put the infinity to here, it's legitimately equal to 0, and you can just supply your work on the side, especially on the exam also, because otherwise you just have to do things carefully. Yeah. Anyway, to continue, we plug in 2, so we have 2 minus. We have the second one is 1/3 ln absolute value, putting 2 in there, 2 minus 1 over 2 plus 2. So here we have 2 plus 2, like so. All right, so now this is 1 over 4, and then we have pretty much 1/3 and all that stuff. So all in all, here we go. This is negative 1 over 3 ln of 1 over 4, like this, right? So it actually is a finite value, so that means this right here converges. And the truth is, let me ask you, is this a positive or negative number? This is actually a positive number. Why? Because if you look at 1 over 4 as 4 to the negative 1 power, this is negative 1/3 ln of 4 to the negative 1 power. You can bring the power to the front, and that's not power rule, so just don't subtract 1. You actually get a 1/3 ln 4. So this right here is the answer. I will leave it like that, 1/3 ln 4. So that should convince you guys that it's positive, right? Because remember, ln if the input is in between of 0 and 1, you get a negative output. Alright, now for second one, maybe you can take a guess if this converge or diverge. That one converges already though. How about this one? Well, let's just go ahead and do the work. You don't have to repeat the same integration, so I will just put down the result right here. This is 1/3 ln absolute value x minus 1 over x plus 2. And we have going from 1 to 2 this time. Alright, putting 2 and putting 1. But remember what we talked about if we have x is equal to 1 right here. This will have a vertical asymptote. So right here, this is technically 1 plus. And if you wonder why it's 1 plus, why not 1 minus? Because you're going from 1 to 2. Right? You're going from 1 to 2. And you have to avoid 1. And to do so, you just have to start a little bit, right? Just a little bit before 1. So this is 1 plus up to 2. Right? Just like that. So that's why. So that's the idea. Alright, so putting 2 and putting 1 plus and see what happens. 1/3 ln absolute value 2 minus 1 over 2 plus 2. That's the first part. And then minus, we have 1/3 ln absolute value 1 plus minus 1 over 1 plus 2, like so. Alright, let's see if we can draw a conclusion on this one or not. This right here is this, right? So we know it's just going to be 1/3 ln 4. So that's great. But for this, if you focus on the inside, 1 plus minus 1. This is 0 plus. And 0 plus divided by whatever is just going to be 0 plus, especially this is just a finite number. So you are really looking at ln of 0 plus. And we will end up with negative infinity. Negative 1/3 times negative infinity, we end up to get plus infinity here. So this right here is finite plus infinity. Oh wow, this turns out to be infinity. So in this case right here, it actually diverges. Notice that this time we have square root of x squared minus 1 on the bottom. Don't do partial fractions because we have the square root, right? But here we can actually do tricks up, and the correct substitution is let x to be secant theta, right? And then you see that this way, dx will give us secant theta, tangent theta, and of course you have the d theta right here. Perfect. Now go ahead and just plug in everything into the original integral, and it depends on how you want to do it. You might want to finish everything in the theta world, and if you want to do that, well, here is x is equal to 2, and here is x is equal to infinity. So you have to just do this one very carefully. And it's up to you, right? It's really up to you to see if you want to work out the trick or not. I will not do that actually, because if you put 2 right here, the first question that you get to ask is that how do I solve secant theta is equal to 2? Likewise, if you put infinity right here, you ask like, how do I solve secant theta is equal to infinity, right? It might be better if we just use tricks up, just go to the theta world to finish the integration, and then come back to the x world and then do everything there. So let's just ignore the numbers right here for now. So with that being said, let's just focus on the integration. Here we have 1 over square root of, and this right here is secant theta, and we have that being squared, and then we have the minus 1, and the dx is all that, so I'll just write down secant theta tangent theta d theta, like so. Alright, what's secant squared theta minus 1? Tangent squared theta, right? So this is just square root of tangent squared theta, and yes, they will cancel, so we have a tangent theta on the bottom. And the best part is this and that will also cancel. In another word, we just have to integrate secant theta. So this right here is the integral of secant theta d theta, which is going to be ln absolute value of secant theta plus tangent theta. Don't worry about plus c because we are going to plug in numbers. But we do have to worry about going back to the x world. Again, that's just my recommendation, especially when you are doing the trick substitution. go back to the x world and then work out the numbers there. Well, we know that secant theta is equal to x. So we can write this as secant theta equals x over 1. And then draw the right triangle. And remember, secant is, well, let's put down the right angle here and then the angle theta. Secant is what? Hypotenuse over adjacent. And the opposite is you open the square root first and you do the hypotenuse square minus this side square. And yes, you see the same radical again. Yeah. All right, so based on this triangle, let's go ahead and figure this out. This is ln absolute value. Secant theta is just going to be x, right? That's the nice one. Good. And then plus tangent theta. Well, tangent is opposite over adjacent, so we have just square root of x squared minus 1 over 1. So this over that. So we have this x squared minus 1. All right, so that's actually our answer for that integration. And then we just have to plug in numbers. So let's go ahead. We are going to plug in 2 and then infinity. Well, plugging infinity, here we get natural log of infinity plus square root of infinity squared and then minus 1. So this right here is the first part. And then minus plugging 2 into the x. We have ln absolute value 2 plus square root of 2 squared minus 1, just like that. Again, we don't need the absolute value though, because but we can have it, doesn't really matter. And you know what's happening. This is infinity plus, this is infinity, minus 1 still infinity, square root of infinity still infinity. You can make it wrap with the sum for that already, but anyway. ln infinity is infinity. So the first part here is infinity. Second part is, well, it's a number, it's a finite number, ln of 2 plus square root of 3. So infinity minus that, the infinity unfortunately will overtake that. So this right here diverges. So I'm just going to write it down right here for you guys. All right, we did the hard work already though, because we used the trig sub to get the integration right here. So we'll come back here and do the same thing. Just use that and then put it down and then figure it out. Well, this is ln absolute value of x plus square root of x squared minus 1. And then we have to go from 1 to 2. And here we are going from 1 to 2, but when x is equal to 1, that will give you a vertical asymptote. So the technically here is 1 plus to 2, right? But anyway though, go ahead and plug in, so you get ln of 2 plus square root of 2 squared minus 1. That's the first part. And then minus ln absolute value 1 plus in there, and then plus square root of 1 plus square, and then minus 1, like so. Right? Okay, the first part, we get ln of, the inside is positive, that's why I changed to parentheses. This is 2 plus square root of 3. And then minus, have a look. 1 plus square is still 1 plus. It's like 1, right? And then minus 1 is 0, square root of 0 is 0. In the end, you get ln of 1 plus, which is like ln of 1. So all in all, this right here is just 0. Very nice, huh? So finally, this right here converges, and it converges to ln of 2 plus square root of 3. When we have a finite number, that will be your answer. Yeah. To integrate 1 over x square root of x to the third power minus 1, you know I like to ask these kind of questions. Don't do trig sub, u sub is enough. So have a look. I'm going to let u equal to the square root part. So square root of x to the third power minus 1. And then differentiate this. We get du equals, well, we get the derivative of the square root is 1 over 2 square root. And then we have x to the third power minus 1. But don't forget the chain rule. Multiply by the derivative of this. So we get 3x squared right here. And we still have the dx. And then we are going to multiply by its reciprocal on both sides. So we get dx by itself, and that's equal to 2. And we have the square root of x to the third power minus 1 over 3x squared. And we have the du, like so. Now, we actually have a really good choice in between of finish everything in the u world or just do the integration first in the u world and then go back to x and then take care of the limit. Up to you. In this case, I think it's okay to finish everything in the u world because when x is equal to 2, we can plug into here, we can figure out what u is easily. And when x is infinity, again plug in here, we know what u should be, pretty easily. So let's finish everything in the u world. In that case, we will have to change the limit of integrations. When x is 2, plug in here, 2 to the third power minus 1 is 7, and then take the square root, so we have square root of 7. And then we are going to put infinity to here, to the third power minus 1, and then square root that. It's still infinity. So u is still going to be infinity. Alright, now we have what? 1 over this x, and this is our u. And then now dx is this portion. So we are going to multiply by 2/3, right? 2/3. And this guy, have a look. This is square root of x to the third power minus 1. And in fact, that's our u. So we can actually just put down u right here. Why do we want to do that? Because they cancel out. And then the problem here though is that we still have the x squared right here in the u world. And you know x is not invited in the u world. But it's okay, it's an easy fix. We can change it real easily. Let me write down the 2/3 all the way in the front first. So here we have 2/3, and we have the integral going from square root of 7. And I'm just emphasizing that we will finish everything in the u world. And then we have u to infinity, that u is equal to infinity. And we have 1 over x to the third power in the u world. Right? And to really take care of this business, we will have to just go back here. Notice we can square both sides, and in that case, we get u squared equals x to the third power minus 1. And then add 1 on both sides. So we can see x to the third power will be u squared plus 1. So we can actually put this right here, and then we can integrate that. So here is 2/3 integral, and we are going from square root of 7 and to infinity, like that. So here, we will have 1 over the x to the third power is just u squared plus 1, and then du. Not so bad. So now have a look. Here we get 2/3, and 1 over u squared plus 1 in the u world gives us precisely inverse tangent. And the best part is that if you put down u, right, and if you change the numbers right here already, you can just plug in these numbers. If you haven't changed the numbers right here, if you put down u, well, you just have to put down this expression, and you will still end up with the same thing. Anyway though, so we have inverse tangent of u right here, and then we are just going to be plugging the numbers. So here we have square root of 7 and then infinity, right? So let's see. I might not have enough space. I'll just keep writing down like this, right? So here we have 2/3 inverse tangent. We put infinity right here. And remember, we are taking the limit, right? And then minus the second part, putting square root of 7. So this is 2/3 inverse tangent of square root of 7, like so. Alright, now here is the deal. What's inverse tangent of infinity? This right here approaches pi over 2, right? So that's actually very nice. This is finite. That integral actually converges. But you might be wondering what's inverse tangent of square root of 7. You just have to know some nice angles, such as inverse tangent of 1. Like for example, you just have to know the inverse tangent of 1 is pi over 4. And this is a really common one. And then I'm also going to ask you guys to try to figure out the inverse tangent of square root of 3. I think you guys can also figure this out as well. Think about it, leave a comment down below. Is this pi over 6 or pi over 3? Notice that these right here are just the special angles. But when you have square root of 7 like this, we'll just leave it like that. That would be totally okay if you do that on my exam. Unless this is also a special angle, you can tell me the angle of this right here turns out to be like 13.75 degree. I don't know though, I just made that up. Anyway though, 2/3 times pi over 2, the 2's cancel, so we have pi over 3, so that's very nice. And then minus, this is still a finite number, so 2 over 3 inverse tangent of square root of 7. So this right here is the first one. So it actually converges. Very nice. Now, have a look right here. When x is 1, we get vertical asymptote, right? Because we will produce a 0 in here. Alright, fine. Alright, I'm just going to pick it up from here because it's going to be the same integral. So this is going to be 2/3, and we have the inverse tangent, right? And now, here I use u, and u was equal to that, so I'm just going to put in square root of x to the third power minus 1, right? And of course, in this case, we are talking about when x is equal to 1 to 2. Plugging, and technically this is 1 plus, but doesn't really matter that much. Anyway, plugging 2, let's see what we get. This is 2/3 inverse tangent of square root of 2 to the third power minus 1, and technically you should put a little parentheses. Alright, so that's the first part, and then we have to minus. The second part is putting 1 plus in here. So 2/3 inverse tangent of square root of 1 plus to the third power and then minus 1, like so. Alright, this right here is what? 1 plus third power, or 1 plus third power is still 1 anyway. Minus 1 is 0, so this thing is actually just 0, so this thing is bye-bye, right? So that's actually very nice. This right here converges as well, because whenever you have the trouble place, that gives you a finite result, like 0, whatever, you know the rest will be fine. And for this, it's just that, right? It's just going to be square root of 7. So this is 2 over 3 inverse tangent of square root of 7. Yeah. So, very cool, huh? In this case, when we have the type 1 or the type 2 situation, they both converge. They both converge. Check that out. First, we know the standard result for the integral of tangent x, which is just ln absolute value of secant x. And now we are going to go from 0 to infinity. But remember, when we put infinity into the function, we are talking about the limit, right? So pay attention to this one. If we just write it down as ln absolute value of secant infinity, and then because that's the first part, let's put a parentheses around it, and then minus parentheses ln absolute value of secant 0. Well, what is ln of, what's secant of infinity? How do we do this one? Well, whenever you are in doubt in terms like about limits or whatsoever, one of the best thing is to look at its graph. So let's go ahead and just look at the graph. So let me just remind you guys, maybe you haven't seen this for a while. The graph for secant x is like this. It's like this, and then like that. And it has a lot of the u's, right? And it has a lot more, of course. And when x is approaching infinity, this right here is behaving really, really wildly. In another word, there's actually no limit for that. So this right here, it's not infinity though. Does not exist. And of course, when you have ln of does not exist, that just does not exist. But by the way, I just want to give an honorable mention. Secant of 0 is equal to 1. But that doesn't matter if you have does not exist, plus or minus or whatsoever. This right here just doesn't exist. Because keep in mind, whenever we are doing an improper integral, we have to take the limit, and the limit we might get a situation that does not exist. But you don't have to be saying anything crazy, because as long as you don't end up with a finite value for the improper integral, you can just say this integral right here diverges. But you cannot say it diverges to infinity anymore, right? You cannot say that. You can just say it diverges and walk away, that's all. Now, have a look right here. This time we have from 0 to pi over 2. Why is this improper though? Okay, yes. We have a vertical asymptote at pi over 2. Very nice. Right? So just as a reminder, when we have the graph for tangent, it looks like this, right? So it's a bunch of these guys. And when x is pi over 2, it's right there. So we have a vertical asymptote. That's why this right here is improper. Always mention the vertical asymptote when you are dealing with the type 2 situation for the improper integral. Alright, for this, again, natural log, absolute value of secant x, and then plugging 0 to pi over 2. But technically though, this time, because we're going from 0 to pi over 2, this is pi over 2 minus, right? We're approaching pi over 2 from the left-hand side, like right here. Right, so that's the pi over 2, a little bit to that. Alright, here we have ln absolute value of secant pi over 2 minus, and then that's the first part, right? Minus the second part, ln absolute value secant 0. Alright, this right here is 1, ln 1 is 0, so all in all, this is just 0, that's nice. But the question is, what's secant of pi over 2 from the left hand side? Well, we're going to look at the picture again. So the thing between secant and tangent is that they both have vertical asymptote at pi over 2 right here. And if you go to pi over 2 from the left hand side, you see that the graph right here, it goes straight up. So in fact, secant of pi over 2 minus this right here gives you infinity. And then when you do the ln of infinity, this right here gives you infinity. Infinity minus infinity, this right here gives you 0. No, just kidding. Infinity minus 0 gives you infinity. So in this case, yes, it also diverges. And in this case, you can say this improper integral diverges to infinity. But earlier, you cannot say this right here diverges to doesn't exist. Don't do that. Hopefully this video helps, and if you have any questions about improper integrals, leave a comment down below, let me know, right? And